So how would we go about using the chain rule, which is what we called the derivative of nested functions back in single variable calculus? How are we going to expand or generalize that approach and those techniques to functions where you have two variables? All right, let's take a look at some examples. So one of the things that we would understand is if we have z is a function of x and y. So let's start off with that. This is like our volume is a function of pressure and temperature. So these are the two first parts of our influence tree, if you like. And pressure and temperature. So these are the direct inputs. From our linearization, we can say that, oh yeah, the change in z is the x derivative with respect to z times delta x, y derivative times delta y. And then the individual members that go before that, let's say we had time as the central function driving both x and y, we could talk about that relationship. Pardon me, let's make that t a little more legible. There we go. We could break down the relationship of t and x in the same way. So x is g of t, so the changes in x are going to be driven by the derivative of g times delta t. The changes in y can be approximated by the rate of change of y with times delta t, and some extra values in there. What we can do is combine those by saying, oh, here's our delta x formula, delta z formula rather. It involves delta x and delta y, but I now have a formula for delta x, and I now have a formula for delta y that introduces the time variable. So now we can write out a big long description of the change in z as a function of the change in time. And if you look at those ingredients, we've got the derivative of z with respect to x, and g prime of t is the derivative of x with respect to time. And that lets us take a look at the ratios that we're looking at. What we're going to do is take this relationship and just divide everything by delta t. So bring the delta t over here. And that, if we let delta t go to 0, is going to be yet another derivative. And it's going to tell us that the derivative of z with respect to t is the partial derivative of z with respect to x. So again, going back to our maps here, if x changes, then z changes. So we need to encapsulate or incorporate that when we're talking about the rate of change of z. Z also changes when y changes. But how does that relate back to the original variable we care about? Well, x is changing with time and y is changing with time as well. And you notice this nice sort of fractional perspective on this, very much like the chain rule. One variable, the organization is z changes with x and then x changes with t, or you can think of almost canceling these fractions. I hesitate to go too far down that road with multiple input variables simply because we wouldn't need two different fractions here, because there's an x and a y contribution. If we try to cancel things, we just end up with two dz dt's and one on the left. It gets pretty weird pretty quickly. It's better to think of it as, why does z change when t changes? Z changes when t changes because x changes in the middle, and it also changes because y changes in the middle as an input to z. And if we just follow all the paths between t and z, each path will give us one term of t changes, so this changes, so z changes. T changes, so y changes, so z changes. That's how you can construct the set of values that are required to find how does my final output change with time? At what rate is it changing over time? Again, pretty abstract. Let's bring this back down to concrete terms. We had two partial derivatives, or two regular derivatives. Note actually that these are regular or full derivatives. Why? Because p is some function of time, and it only has one variable as its input. So if we only have one input variable, then we use the regular derivative just like we did in the fall term or the first term. And if we had two variables, then we'd use the partial derivatives. And for that reason as well, let's take a look at our equation here. PV equals nRT, and we're using a couple of features here, that n equals 1, and that V is our output. So our volume is RT over P, like so. And from that, we can say that dV dt is the partial derivative of volume with respect to, sorry, let me highlight this point here. This is a constant. So this is really a function of temperature and pressure only. They're the only things that change. So we'd have, how does our volume change over time? At what rate is it changing? Well, it's changing at a rate dictated by how the volume changes with temperature, and then how the temperature, changes with time, and then the partial derivative of volume with respect to pressure, and then, well, how quickly is the pressure changing with time? Again, going back to our diagrams, the time affects both temperature and pressure, and temperature and pressure together influence the final volume. There we go. All right. Once we have all this information, what do we do? Well, we can determine all these values. In fact, some of them are given. We've been given these rates here. We've been given these rates, that rate there. And this partial derivative is going to come from our formula by differentiating it. So let's focus on that. We need to find the partial derivative of volume with respect to temperature and partial derivative with respect to pressure. Well, those we can obtain simply by differentiation. The temperature derivative, with all the practice we've had so far, that should be straightforward. T is the variable, R and P are constants. And the partial derivative with respect to pressure. Pressure is in the denominator, or P to the negative 1. So we're going to get negative 1 RT P to the negative 2, or P squared in the denominator. Now, what else can we do to elaborate that? Well, we need to know not just the rate at which things are changing. We need those for sure. But we also need to calculate this rate at the particular instant we care about. So we're saying, all right, let's visualize the scenario for a moment before we continue with the calculations. We're at a certain pressure and we're at a certain temperature. So we have a certain state of being. Then someone is dialing up the pressure and dialing up the temperature. And just in terms of the physics of this, you can imagine, okay, if I increase the pressure, the volume should go down. If I increase the temperature, the volume should go up. We're doing both at the same time, so we're expecting some kind of trade-off. The volume will either go up or down depending on how these rates relate back to the actual ideal gas law that we're working with, and in particular through the rates of volume changing with temperature and volume changing with pressure. And hopefully we'll see that play out in the calculations. That there's a trade-off about as pressure increases, our volume is fighting to go down. As temperature increases, the volume is, as a result, trying to increase, and there's going to be some balance between those two. Let's include then the pressure values that we have and temperature values that we have, 320. And our rate of change of volume with respect to temperature is R over P, or 8.31 over 20. Our pressure derivative is 8.31, that's R. Temperature, 320 over 20 squared. And with all of that, we now have the four ingredients that we need to find how is the volume going to be changing as time changes. Let's plug in the values. dV dt, 8.31 over 20 times 0.05 and negative 8.31 times 320 over 20 squared times 0.15. Notice what you're seeing here. This is T increases leads to a volume increase. That's going back to our physics or going back to the calculations here. We're increasing the temperature, and increasing the temperature has a positive coefficient out front here that'll increase the volume as a result. Notice this negative sign here. When we increase the pressure, or as time increases here, we increase the pressure, and that causes a decrease in the volume because of that negative rate. We're talking about a derivative, we're talking about rates, and those rates are negative here. That, I think, this stage, I think, summarizes what we really care about most. We're going to calculate the value just for thoroughness, but it's understanding these pieces and understanding how they fit together is the most crucial thing. With a bit of calculator work, we end up with the value 0.976. Now that value has units associated with it in an example like this, in a modeling application like this. From our derivative here, the natural units would be liters per unit time, which would be seconds. And it's worth studying the units and how they also work out with these derivatives. This is liters per second. What's the rate of change of volume with respect to temperature? Well, that's liters per degree Kelvin. How quickly would my volume change if I increase the temperature? And of course, the rate of change that were given earlier was degrees Kelvin per second. And so we see the units cancel out nicely. Likewise, when you have kilopascals per second, and over here we have liters per kilopascal, how does the volume change with pressure? The natural units would be liters per kilopascal multiplied by kilopascals per second, and both of those terms will end up at the same units of liters per second. So this is the kind of problem that gets much easier with practice. The key thing to try to understand at this stage is just how you would write out this expression for the chain rule for a function like volume in this case here. And it typically starts with a statement, very much like related rates in fact, a statement that's always true, and then differentiating that to obtain some relationships between the variables, rates of change of your output to your inputs, and multiplying by then the rate of change of those variables with what their inputs are. Again, there's good practice in the assignments, but the key thing is to look for structure in this chain rule so that you can apply it appropriately in your future examples.